here. Yeah.
Everybody's here and ready to go, Professor.
Okay, good. Oh, yeah, it's 8 a.m. Yeah, we can get started. Hi, everyone. So my name is Peter. So yeah, I'll be your instructor for this course. So as you can see, it's called Partitions in Mathematics and Physics, right? And well, so today will be some introductory lecture. So I mean, I can as well give this lecture in in the middle school or even in elementary school, but sort of I can ask different questions. So this topic, I like this so much because it's so so partitions appear in various parts of mathematics and physics, and to understand what they are, you pretty much don't need any background, right? So they're so exciting and so interesting. So today will be kind of so yeah, the format of today's lecture will be more like of a discussion. So I will be asking the questions, and I hope you will answer them. Yeah, and you're gonna like the topic, and then we'll see where we can go. So like I have an approximate syllabus in my head, but like depending on with each of your interests, we can adjust our kind of trajectory further down the road. Okay. So okay, let's get started. So does anybody know what a partition is? Like in math. So it has part in it, right? But part of what?
I can take a try. So basically, it's like with integers, if you're using like 4, it would be 2 and 2 or 3.
Good, exactly. This is what they are, absolutely. Yeah, so these are ways to decompose an integer into sum of smaller positive integers. And just a way to do it is called a partition. So with 4, as Emily was saying, it's 1 plus 1 plus 1 plus 1, or 2 plus 1 plus 1, or 2 plus 2, or 3 plus 1, or just 4 itself. So you can write 4 plus 0, but you don't have to. You can just keep with 4 equals 4. So 4 will be as a part of itself, right? So those things are called parts, right? So and it's very convenient sometimes, and sometimes it's even, as you'll see later, to use those diagrams. I call Young diagrams, and I hope the notation is pretty clear. So here, the height of each of those columns is just the size of each part, right? So 1 plus 1 plus 1 is the row column. 2 plus 1 plus 1 is this hook, right? And so on. Now, here's the question: do you think, are they uniquely defined? Are those partitions uniquely defined? Just speak up. No need to raise your hand. We are like 5 people or 6 people.
I'm sorry, could you repeat the question, please? You're cutting off.
Oh, are they uniquely defined? So I mean, 2 plus 1 plus 1 is the same as 1 plus 2 plus 1, right? But the convention is that we're going to draw the first part, the largest part first, or like, so they should not be decreasing. So so 2 plus 1 plus 1 is the same partition as 1 plus 2 plus 1, and so on. So the columns of those Young diagrams will be non-increasing. So they can either stay the same or they can drop, but they never go up. Okay, so it's a convention. Okay, sounds good? Good. Now, well, let's practice a bit, right? If you haven't seen this before. So yeah, maybe. Okay, let's find partition of. Okay, so here's the answer for 5, and I'll let you guys do 6 yourself. So with 5, you have 7 partitions. So there'll be a function p of n, which is the number of partitions of n, right? So p of 5 is equal to 7. Here are the 7 partitions of 5, right? It's 1 plus 1 plus 1 plus 1 plus 1, 2 plus 1 plus 1, and so on. Okay, so given this in mind, can you find partitions of 6, and how many of them are? I hope you guys have some pencil and paper somewhere to write, to draw.
11.
Yeah. You got answer. Zo, is that the pronounce it right?
Yeah, you can just okay, just is 11 right or
11 also possibly. It's okay. So you can maybe give us the let's put them on the all down. Okay, so can you give us the first one?
might start with 1 plus 1 plus 1 plus 1 plus 1 plus 1.
So like all ones, right? Like it will be the 6 ones.
And start with 2, like 2 plus 1 plus 1 plus 1 plus 1. And 2 plus 2 plus 1 plus 1 and 2 plus 2 plus 2.
Right. Okay. Maybe we can actually do something better. So far, all the diagrams that you told us, they look like this, right? So they look like, so we add a block here, right?
Yes.
And we add a block here and add a block here. And so yeah, so first time would be just adding those blocks here at the bottom, right?
Yeah.
Good. So that gives us 7. Now, which ones we missed? What are other partitions which are not in this list?
Or 2 plus 2 plus 2 is not in
Right.
this.
So it was not in the list. Is this one, right? Like this, okay.
And well, 3 plus 3 is not in this list.
Exactly. So which one is block looks over here? Yeah. So you can do a 3 plus 3.
And 4 plus 2.
Right. Which this one is over here. So you can see using diagram. Did you do the numbers, or did you do the diagrams when you derived your answer? Did you use the diagrams, or did you just said one played with numbers?
By number, just
Good. So I think 11 is the right answer, but you can see with diagrams it's much easier, right? So it's easier to visualize what's going on here. You can basically see what else you need to add, right? So we have 10, and we need one more, right?
Itself.
Like the column, right? So it will be 6, like this, right? Does everybody agree? Right. So in fact, I think we have I have them all here. So let's remove the annotation. So you can see that you can kind of understand this couple of ways. So one of them was just to add another block here, right? So you can see as we move from left to right in this picture, it's like taking block from the rightmost block and throwing it all the way to the left, such that the rules of making partitions are satisfied, right? That's how you can get 1 plus from 1 plus 1 plus 1, you get 2 plus, etc. Then you take another block, and here you have a choice, right? You can put this block here to get this diagram, or you can throw it all the way there to get this diagram, right? So there's like this is called Hasse Diagrams, right? Which corresponds to the partly ordered set, right? So there's like, you can draw those arrows. In fact, I think they're on the first slide. So here. So you would there's certain order, at least partial order, in how to build those partitions, which may be helpful for the future, right? So and then et cetera, right? So or if you like, you can start with this column and you can knock down blocks. You can take the topmost block, put it down, take the next topmost block, either you can put it down either here or there, and so on and so on. So with 5 there are 7 options, with 6 there are 11 options, right? So P of 5 is 7, P of 6 is equal to 11. And you see that there's this nice symmetric partition with a 1, 2, 3, which looks like staircase. There's this window 3, 2, window 2, 3, and so on. So we'll try to study as many properties of these partitions as possible. And as you'll see, a lot of them will be, you can understand just by looking at these Young diagrams. Okay, so yeah, any questions here? Yeah, just ask questions that they know. Good. So these are, it's a picture from Wikipedia, which I turned 90 degrees, right? Now, if you look at the books and papers, there are different conventions to draw Young diagrams. So This is so-called, French/American convention. There's also what's like German, where instead of making them like a hooks at the bottom left corner, you would draw them like like this. So they would hang over, like icicles. So and then the rule in sense is inverted, right? So you need to, so that they just sort of dangle down. Right? And then also Russian notation, which is actually quite interesting because it's used for something for some other applications. You would turn it 90 degrees. So you think of this as like a corner with a 45-degree angle here, and you would throw blocks in them, right, like this. And basically, as long as those blocks can stay stable in stable way, it's a partition, right? So, and the reason why you do this is because you would then want to project those down onto this horizontal axis and do some counting. Right? For example, here you can count how many blocks you have in each of those projections. You'll have 1, 1, 2, 2, 1, and the partition itself is, well, depending on how you look at this, is 3, 2, 2. So there are various ways to look at those Young diagrams. Okay, moving on. Yeah, so these are the partitions of 8 from 1 to 8, right? So 8 is the most one, and you can see how this sort of partial ordering plays out. So like there's always kind of those corner partitions or the square partitions in those corners, and then there's a certain symmetry, right? So those which go here and there, they're related by just the 90-degree reflection. Excuse me, the mirror reflection relative to the diagonal. So we'll talk about this reflection later today. We'll talk about the symmetry properties here. Okay, good. So we'll look at, come back to this picture later to do some counting. Okay, so there are various kinds of partitions, you see. Now let's talk about some of them in more detail. Yeah, so right, here just some numbers. And in fact, if you guys use Mathematica, let me just show you. There's a function which allows you to generate those partitions. 1 second. I should load it, yeah. So just 1 second. It's not in partitions. It's okay. So yeah, so for example, it returns number of partitions of returns the function p of n, or there's a function partition list. Partitions. Where is it? I just had it. The partition p, integer partitions. Integer partitions. Say it returns you the list of all integer partitions of any number. So and then so these are partitions of 10, right? So then so you can see that the list grows pretty far. So if you'd like to, you can make a table of those. So by the end of today's lecture, maybe mid tomorrow's, we should be able to understand this counting. Okay, we'll see how much it will take. To say, here's the list of the table of this function p of n. It's a sequence. Actually, I probably shouldn't have showed it to scale. Let me just show till 6. Okay, so see it grows like this: 1, 2, 3, 5, 7, 11, and then you can kind of continue it on, right? So 10, maybe 100, right? So it grows pretty fast. So p of 100 is 190 million, right? And yeah, so there is no formula for this partition, so you cannot just say that p of n is equal to stuff. But there is a recursive relation, and then there is well, There's several kinds of recursive relations. Yeah. Good. So yeah, so if you have mathematics on your computer, or you can just go to Wolfram Alpha, right? So there's an online resource and play with those partitions at home. So for some of the homeworks, you may need these partitions. If not, I'll provide you the list. Okay. Let's get back to our stuff. Okay. So yeah, so it's P of 9 is 30. So let's try to understand this pattern of functions P of n. Now, our first observation will be about the odd and distinct partitions. So what's an odd partition? It's a partition whose parts, all of them are odd. So this partition is 3 plus 1. 3, 1. 3 is odd, 1 is odd. Very simple. Every part needs to be odd. So 3, 1 is odd, 3, 2, 1 is not. And second type of partitions are distinct, meaning that all parts are different. So 3, 2, 1 is a distinct partition, or partition with distinct parts, right? This is not, right? Because it has, it is agency. Yes, so this is 4 to 1, it's not a distinct partition. So let's do two exercises. So first we'll count the number of the odd partitions. For every number, say from 1 to, say 8. We're going to use that table from Wikipedia. Count the number of odd partitions, and count the number of distinct partitions. And then we'll see what's going on here. So maybe, I want to go back 1 sec. Let's first go back to here. So can you guys annotate? Let's see, I think, can I enable? Yeah, you should be able to annotate. So if you like, you can write your numbers next to each of them. So next to each of those groups of pictures, write 2 numbers, the number of odd and number of distinct. So for example, here, right, for n equals 4, let's count them together. So this is 1, 1, 1, 1. So this is odd, but not distinct, right? So 2, 1, 1 is neither. 2, 2 is, neither. 3, 1 is odd and distinct, right? And finally, 4 is distinct. So we have two odd, right, and two distinct for n equals 4. Let's count the rest and make a table. So how many odd and distinct you have for 5, 6, etc. So some of those partitions are odd and distinct at the same time. So we should count them independently. Yeah, if you like, you can either annotate, you can write on your paper, and then we'll compare things. Is the connection fine, by the way? I think somebody complained that I was cutting off. Is it okay now? Good? Okay. Okay. Can I grab a notebook to write in? Oh, what do you mean? Can you grab a notebook? Of course you can grab a notebook. I mean, you want to go somewhere? Sure. Yeah. Oh, I just saw the message. Okay. Whenever ready, you're welcome either to send me messages in chat or you could just annotate on top of the screen instead of. So Michael sent me his answers. Okay.
Should we send the
That's what I think. But yeah, so yeah, just send me like a sequence of two numbers. Say for 4, for 5, for 4 we have say 2, 2. For 5 is what?
So for 5 and 6.
Okay, so let's check. So Michael's saying for 5 you have found 3 distinct, and for 6 are 4 and 4. Okay, so it's 3. Oh, sorry, it's a 3, 3 here, right? 3, 3, and for 4, for 6, it's 4, 4. Do you have the same? So let's check the 4. So it's like, so this is odd. This is odd. What else is odd? 5, 1. This is odd. And 3, 3, right? So this is odd, right? So there are 3 odds, 4 odds, and distinct. This is distinct. This is distinct. This is distinct. This is distinct. Yeah. Now you can see sort of distinct partitions, the kind of the cluster around those like this right tail. So distinct, 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 not distinct, distinct, distinct. This one, I mean, the one on the right. So 5, right? Kind of those distinct partitions are easy to count from columns, right? So when you sort of take those blocks and throw them down, right? Sort of as long as you have the sizes of which columns are different, then you're good. Again, in so for 8 goes like 6, 6. So do you see the pattern? What's going on? So the numbers are equal, right? Well, so why the hell is this true, right? So let's try to understand. Okay, just for fun, let's maybe do, okay, so maybe let's do one for 9. So if you like, you can annotate, you can circle from this list, you can circle partitions which are odd, and then maybe with a different color, you can circle the partitions which are distinct. So kind of trying to visualize the partitions using using numbers. Can you annotate, guys, or not? You should be able to turn on the annotation tool, right? There's like a pen.
If we annotate, does everyone see it or is it?
Yeah, yeah, everyone sees it. Yeah.
Okay.
What color should you
Pick anyone.
use?
It's usually not the problem. So
We need to use the same color.
oh, come on, just yeah, we'll figure it out. It's not that complicated. There are like 6 people. It's not 50. Yeah, so 9 is both odd and distinct. Right, so see here that yeah, so the way the order here is like, yeah. Mm-hmm. So how many of each do we have? So it's 1, 2, 3, 4, 5, 6, 7, 8. Is it 8, 8? I see 8 and 8 of each. Is that right? Yeah, looks like there are 8 of both types. Okay, good. So yeah, you can obviously see that there's a pattern. So our task will be to explain it. So yeah, okay. So I think so you got the idea. So we don't need to repeat this exercise anymore. Here's the table so far, right? So the P of n versus number of odd partitions versus number of distinct partitions. So clearly, these last two rows, they grow slower, right, than the number of partitions itself, because there are much fewer distinct partitions or much fewer odd partitions. So let's try to understand why these partitions, the number of those types of partitions are the same for every n. Right? So it's a pattern. Now we need to prove the theorem. So theorem proves that the number of odd partitions is equal to the number of distinct partitions. Now here's the summary table, which will hopefully help you to navigate the proof. So look at those parts and see how would you provide the one-to-one correspondence, right? So to prove the theorem, you need to provide a recipe like the dictionary, the one-to-one correspondence. So how from one partition to map another partition, and the rule must be universal, right? So it should apply for every for every number, for every n. Yeah, so you can look at them carefully, and then once you're ready, you can again annotate with arrows, like which partition goes where.
Professor, I have a question.
Yeah.
So, wait, is it okay if I annotate?
Sure. Yeah. Yeah, let's try and see what's your idea.
So like, is this partition, and this one
Oh no,
similar?
those are different n, right? So it's n equals 5, 6, 7, 8, and 9, right?
Oh,
So
okay.
the rule must be within each number, of course, right? So it's like 5 different examples.
Okay, I got it.
Sure.
Thank you.
Professor.
Mhm.
So what we need to prove is the case of all values of n.
Well, you
And-
need to show me the recipe, right? Like so you have partition, K1, K2, K3, and so on. Which partition on the other side is it mapped to? Yeah.
Okay, got it.
But like you don't have to formulate it as abstractly as you'll see soon that the recipe is pretty straightforward. So do it by example is the way to go here, and it's generalizable very easily.
I just have a question. Have you like arranged the left and right side so that they're supposed to correspond with one another, or do we have to make that like?
You have to
Or-
make it, yeah. So as of now, I just made the list, right? So okay. Of 5 things, but I didn't tell you the rule. So I'm not saying that say this should map to this, right? So it might, but you still need to explain the mapping, right? You need to define this map, right? And the map has to be one-to-one. So for example, where does 6 ones go? Do they go to 5, 1? Do they go to 6? Where does 3, 1, 1, 1, 1, 1 go? So once we understand how to do it in those examples, we should be able to do it in general. So say you have partition of any n, say K1, K2, K3, such that sum of those k's is equal to n. And then it will be mapped to partition, say L1, L2, L3, such that sum of those L's is also equal to n. So first one is odd, the other one is distinct. And yeah, so try to make this map as easy as possible. So it may not be unique, but try to make it sort of as concise as possible. So the rule must be very simple and universal. And if you're in doubt, just try. So take maybe this n equals 6, right? And just see what comes to your mind. So where do you want to, what does 5, 1 go? Where does 3, 3 go?
Does 3, 3 go with 3, 2, 1?
I mean, it might, but you need to explain me the rule. What's going on? So why is one of the threes is split into 2 and 1?
I don't know. I think.
Okay, so
like-
if 3, 3 goes to 3 to 1, then what about the rest, right? So kind of you need to say this goes here. Okay, where does 5, 1 go?
5, 1.
Okay, that's simple enough. Good. So let's keep it as simple as we can. 3, 1, 1, 1.
Yeah, I'm not sure. I don't think it
So
works.
maybe you want to amend the first choice. Okay, let's keep 5, 1 to 5, 1 because it's very natural. Let's think together where is more natural for 3, 3 to go, and for the others, right?
Would it be
For-
4? Sorry.
Okay, well then sort of you do something with both. It's kind of both are odd and then both are even, and something strange happens, right? Sort of the okay. So how about let's take one step back. N equals 5. So I think following your recipe, 5 should go to 5, right? Because 5 is odd and distinct at the same time, right? Okay, now we need to make one choice. 3, 1, 1, does it go to 4, 1 or does it go to 3, 2? What's the simplest?
3, 2.
3, 2, right? It requires minimal action. So we just combine those two ones into 2. 1 plus 1 equals 2. Right? It's easy as that. And then, okay, let's keep it for now. And then the 5 ones go into 4 plus 1. What do you think is going on here?
The first 4 ones are being added.
Right. Okay. That's what happens. But can you kind of anticipate, kind of predict what's going on? Like, okay, but maybe let's finish at n equals 6. Okay, so 5, 1 goes to 5, 1. Then where 3, 1, 1, 1 should go now? So let's want to keep 3 intact, like as many, make it as simple as possible.
3, 2, 1.
Okay, good. So we can do it like so. These two guys get together. So 3, 3 goes to
4, 2, or
well, further we discussed it, right? So that looks a bit violent, right? We need to break those 3s into things that then combine together, right? So both are odd, these are even. What's the most natural thing you can do with 2 3s?
Add them together and make 6.
Yeah, to make a 6, right? And then 6 once goes to 4, 2. So it's 4 plus 2. Do you see what's going on? So what is this rule here? What does it do? Okay, maybe let's do 7. So please use your arrows. So now finish the rest of the table. So map those things together and see, and we'll guess the rule. Mm-hmm. Eunice, are you sure you don't want to switch those around? So again, see, there's 3 here, there's no 3 there. See so basically maybe the rule for going from left to right should be that we don't break down things, we only collect them. We collect objects that are alike. So how about we do it? Yeah, we do it like this. Yeah, okay. Yeah, so for 4 to 1s, we go into 4 plus 2 plus 1, and for 3, so this is 3 plus 4. Okay, now let's do the other 2. Well, 5, 3 is good. So I think we agree that if you have the number which is the same, right? So you have 5, 3 in both columns, right? So let's just keep it this way. It's just easier. So adding 5 plus 3 sounds like too much work, right? So do you mind if I erase those? So let's do so 5, 3 goes to 5, 3. So in other words, the rule is that if the partition is odd and distinct at the same time, like 5, 3 and 7, 1 here, then let's just identify them together. That's the easiest sort of isomorphism that you can make. Mm-hmm.
That work because you would do 3 plus 3 and then
Right. Yeah. So, we'll combine them to get
you're
16.
like adding and combining. Okay, I got it.
Good, good. And again about the other two. So what's the most natural combination would be? So see here again, there's a 3 here. So we should probably keep the one with the 3. Yeah. So let's do it like that. Yeah. And then yeah, and then we have wait, 5 to 1. Wait, hold on. 5 to 1. You want to do? I think you want to do this 5 to 1 according to our rules. So because we're just combining things. 5 to 1. And then 8 ones should go to 8, right? Okay. So, do we get it right? Yeah, I think now everything works. Okay, and finally, let's do the last one before we formulate the rule. Yeah, so odd and distinct, they map to each other. So yeah, 531 is already taken. Good, so 711 goes to 72. So you unite or you combine those two.
Professor.
Yes.
I think it's in the row 3. Maybe there's a 1 missing there.
Oh yeah, I think there's a type. Yes, thank you. There's a type, right? It's 9. Should be 9. There's before 4 ones. Yeah, absolutely. I should correct it. Yes, thank you. So this is 5 and 4 ones exactly. And probably that was confused. Yeah, so where the 5 and 4 ones should go? Do you think? Yeah, to 5 4 absolutely. So just combine those four ones together to get a 4. So 531 goes to 531. 3 3 3. So but now there's a choice. See how there's 3 3 3 and then 3 3 1 1 1. And then we need to decide which one goes to 6 3 and which one goes to 6 to 1. So what's the most natural things with 3 3 3? You can combine, if you combine 2 3s, right? So that goes to 3 3. Okay, and then those we can combine those to 1s, and that goes to 6 to 1. It's getting a bit overcrowded. Do you mind if I erase those? I just want to redraw single arrows, right? So this goes to 6 3. 5 3 1 goes to itself. 3 this goes to, and then combine 2 3s here. So that goes to 61. Okay, and then finally 2 more. 3 and 6 ones go to 5 4. Well, hold on. Yeah, so what's 5 4? This goes to, yeah, I forgot yet. So this goes to 5 4. Yeah, these go to each other, and then 6 and 3, 3 and 6 ones, and then 8 and 9 ones. And we have 8 1 remaining, and yeah, 4 3 2. That's right. So it would combine. So this is 4 and 2, and those will be 8 and 1. Okay, good. I think it should have enough information to proceed. So what's the rule? So given an odd partition, how to assign a distinct partition? What do we do? Can somebody summarize? Or backwards, whichever is. Yeah. So you have two sets which are isomorphic. You need to sort of define both maps from A to B and from B to A.
Don't split up the numbers, like don't break them up and make it, don't expand them.
Right, but instead we would combine them, right? So we combine them into what? So just look at those examples. See, sometimes we combine into 2s. Maybe looking at ones, it would be easier. So we can combine them into 2s, into 4th, and into 8th. So all the even numbers that you can see in right column are well, either twos or fours or, well, there are some sixes, but okay, so sixes come from combining threes, like 3 plus 3 equals 6. But if you combine ones, we only get twos, fours, and eights. And probably we'll have other high numbers for higher partitions. So we'll describe a bit more. So we'll do this combination until what? So what's the, so for example, here you have 3, 3, 1, 1, 1. So we combine 3 plus 3. So we need a distinct partition, right? So whenever we have equal parts, we need to add them because we want a distinct partition. So all these equal guys, they have to somehow collapse to each other. So, and then see, for example, 3, 3, 3. We could have added them all together to get a 9, but then we would know what to do with this 9. So instead we do it 3 plus 3 equals 6, and then we'll leave out 3, right? So let's try to formulate the dictionary more precisely.
So when you have like a set of the same number, do you just like try and collapse it into like additions of like the numbers 1, 2, 4, 8? I would think like 16 when we get there.
Mm-hmm.
Yeah.
So
like
talking about ones, if you have ones, then you would collapse them into those numbers. So you said 2, 4, 8, 16. What's common about those? What is this
they're all
sequence?
powers of 2.
All powers of 2, finally. Yeah, so this is a sequence of powers of 2. Yeah, exactly. So if you look in it, so those are powers of 2. So like and in fact, you can sort of use this to go backwards, right? So say yeah, so like you would combine them into powers of 2, right? So for example, you would take you know, so we'll start from left right. So say we take those two ones together, so they give us a 2. Now why do we need to take a 4 next, right? Well, we can combine another 2 ones, but it will be a 2, but we already have a 2. So we would you know, we're gonna have to add another 1 plus 1. So that's how we get 4 from here. That's how we had 4 plus 2, right? And then all other things go the same way. So for example, if you have 3 and 3, you can combine them together. It will be so I mean up to sort of modulo 3, so it will be 3 multiplied by 1 plus 1, right? And so on. So here you can kind of see this idea of on small numbers. So yeah, so the rule will be to combine them into powers of 2. Combine those ones. So let's try to summarize. So you take sort of from distinct to odd. See that's what we're doing, right? So we would that's how this combination goes. So in fact, yeah. So map. Yeah. So it probably easier to formulate the map backwards, right? So you take 2, you just split, right? So you can divide it by 2, so you get 1 plus 1. 4 you can divide by 2 twice because it's the second power of 2. So 4 goes into 1 plus 1 plus 1 plus 1. 6 goes into 3 plus 3 because you just divide by 2, right? So see, it has to be, so if a partition is distinct, let's put it this way, if a partition is distinct, then there are 2 types of distinct partitions, odd or even. If it's already odd, then we don't do anything about it, right? Because it's already odd and that's what we're after. If it's even, we need to divide it by 2, right? If after division by 2, these 2 partitions, they remain even, like in this case, we need to keep dividing. That's how these powers of 2 appear. So you divide by 2 over and over again until you get to odd numbers. So that's how 4 goes into 4 ones, 8 goes into 8 ones, and 6 goes into 3 plus 3. similarly here, there are some more examples. So odd and distinct partition, well, doesn't change because, you know, they're not divisible by 2. But say 6, 2, both parts are divisible by 2, so you divide them into 3 plus 3 and 1 plus 1, and so on and so forth. Right? And then backwards, this is the nothing but the binary representation of those numbers, right? So, for example, if you have 3 ones, you're going to get 2 plus 1 because it's 2 to the power of 1 plus 2 to the power 0, right? So 5 ones will be 2 to the 2 plus 2 to the 0, and 8 is 2 to the 3, right? So sort of the answer to the proof of the theorem is that you're doing a binary representation. So whenever you have a part which repeats itself, say n times, like k times, and taken, then you would write it as a binary presentation of that number, and that's it. So see, it's very straightforward. Questions? Okay. So distinct partitions are the same as odd partitions. Now, our next exercise will be about the symmetry that I mentioned to you, the conjugation. So the conjugated partitions are those which are obtained by mirror symmetry relative to this diagonal. So if we put like this, so then that's why 2, 2, 1 becomes 3, 2. Right, so it's a well-defined operation on all partitions. And now, out of those, we'll look at the very special sort of subclass of symmetric partitions, right, which do not change under this conjugation. Okay. So some of those partitions, very few of them are symmetric. So let's look at this table again and the picture, and then highlight or circle those partitions which are symmetric, and let's count how many of those are for each number. That shouldn't be too hard. In fact, they kind of fall in the corners. I just keep going. Yeah. No. Yeah. So in those cases, there are either 1 or 2, right? So I think it's good. Yeah. So there are the 2 for 8, and then 1 for each of those before it, right? So it's 1, 1, 1, 1, 1, and then there are 2. So see, there are very few of those. Okay, thank you. So you see how Young diagrams are helpful. So you can get things right away. Now, let's do this mental exercise. For 9, I didn't draw you the pictures. Can you find symmetric partitions here? And then we'll make another table. So there will be another surprise. I mean, surprise will come a bit later, but yeah, let's do this one first. Right. So the 333 looks like the digits, the number, this thing, right? So this is symmetric. Good. What else? Yeah, maybe you can try to visualize the diagram and then sort of make. So there should be at least 2, right? Because for 8 there were 2. It's maybe 2. So 5, 1, 1, 1, right? So this, yeah. So indeed, it's like a wedge with 4 blocks sticking on each side, right? So that's 5, 1, 1, 1, 1. Is that it, or there would be the third one? So you may try to understand it by moving those blocks, right? So say it needs to be symmetric. So okay, so what else can you do? Can you say maybe take this block and move it somewhere, right? But then it stops being symmetric, so you need to maybe move another block, and that's kind of hard, right? So, or from here, you cannot make it symmetric by moving 1 or 2 blocks. So it looks like that's it, right? Okay, so maybe there are 2 for 9. They have exercise for 10. Yeah, and let's do one more for 10. So there are 2 for 8, 2 for 9. Let's see how many we get for 10. Sorry, which one is that? 5, 5? 5, 5 is not symmetric. Of well, 5, 2, 1, 1. So good. So that's indeed. So this. Yeah. So it's the same partition as before. Only now we kind of add this block. So that's 5, 2, 1, 1. So it's clearly symmetric. 4, 3, 2, 1. So here we have the staircase. Right. So 4 plus 3 plus 2 plus 1. Okay, that's number 2. Again, you can ask yourself, so say you start from here, right? Can you do anything to, so yeah, so what we can probably do, you can take those blocks, put them here like this, and you'll get this partition. So yeah, so looks like there are also 2 of them. So right, so as you can see, those numbers, they grow pretty slow. However, I mean, okay, in the interest of time, let's not do 11. So there'll be some more exercises I'll do give you for home. Okay, and now let's count the, yeah, so good. So we did, and now let's count another. So yeah, so we had basically the table goes, it's stabilized, it goes to, it's 1, 1, 1, 1, and then for 8 is equal to 2, for 9 and for 10 is 2, and for 11 I think it will be 3. So I'll show you later in the table. And now let's do another exercise. So Professor, just heads up, we're coming on the midnight on Chinese students. Where should I stop? At 9:30, at 9:30, in an hour and a half? Do we go for 2 hours or for 90 minutes?
Typically, the first session will run for about 90 minutes, Professor.
Yeah, okay. So we'll be done like about half an hour. Yeah. So
Brilliant. Just wanted to give you a time.
Sure. Yeah, thanks. Yeah, well, so before I go, we'll do this other exercise, and I think we'll see how to. Good. So the second exercise now, let's identify partitions which are odd and distinct at the same time. So circle those, odd and distinct, so which means that every part is odd, and they're all different. And let's count this number of partitions for each of the. Yeah, then this one for 11 we'll do both. I will be back in 1 minute, just one. Okay, so what do we have here? So what's the number? It's 1, 1, 1, 1, 2, right? Okay, so far it goes in the same LA as the previous story. So it's the same. So far, the number of odd and distinct partitions coincides with the number of symmetric partitions. So by now, we'll probably see where is it going, but let's just play a bit more. So for 9, show odd and distinct. Yep, so 5, 3, 1. And 9, yeah, good. So there are 2, we expect only 2. Good. Now for 10. 7, 3 and 9, 1, right? Yeah. Okay. And let's do 11. So I think for 11, there should be 3 of each. So now let's do both odd and distinct and symmetric. Yeah, so 11, 7, 3, 1. Yeah, so those are odd and distinct. Yeah, maybe with a different highlighter show symmetric. Yeah, so you're gonna have this, right, so good. So right, so we'll have this wedge, so because 11 is an odd number, you can put one of the blocks in the corner, and then we'll have 5 blocks here and 5 blocks there, right? So that's this 6 and 5 ones. So that's one symmetric. Then you can have a 4, 3, 3, 1. So it like we had this 9 guys, and then we put one here and one there. Okay. Yeah, and then right, and then this 7, 3, 1. Okay. Do we still have 2, or there is one more? See if you can kind of move those blocks around to maybe not. 4 and 7 ones. No, I think one hook will be longer than the other hook. So for a 6, 1, 1, 1, there will be 2 equal hooks. Oh, I thought for 11 there are 3. Let's see. Yeah, for 11 there's 2, yeah. So for 12 there are 3. Yeah, okay. So no mind, right? So indeed, so we have them. Sorry, erase that. Yeah, so there are also 2 for 11, and then I hope sort of you can take my word for it. So there are 3 for 12. Okay, let's not do it now, but instead let's try to prove it. So in fact, I think I have a picture for 12. Good. So again, so there's not second pattern that we have found is that the at least in the examples that we've seen so far, the number of symmetric partitions matches the number of odd and distinct partitions, and you can see those numbers to grow slower still, right? So there are only three of each for n equals 12. So let's prove this theorem. And again, so you need to provide a very simple recipe, which is universal. So it's a one-to-one correspondence between the two sets of symmetric partitions and set of odd and distinct partitions. And to help you with this, I drew some diagrams. So all through 11 we did together, and this is the answer for 12. So there are 3 of each kind. Well, try to provide a dictionary. So like, so of course, like when there are 2 and 2 in each, there's not much data to work off of, but I think it's still, I hope it will be enough to suggest the main sort of the idea. just try to think out of the box. Like,
So
yeah.
for the case of odd number, you can just, like for 7, you can just stretch out these blocks and
can you maybe show? Can you draw it or?
Wait, so for like 7, you can just simply stretch out these boxes.
Like straighten out this hook, right? So take a hook and kind of straighten it up, right? Oh, okay. Or here's what you mean by stretching out. So like you want to just put them down, right? The hook that kind of sticks to the right, you're going to put it down like this, right?
Yeah.
Or okay, so right. So here, right. So that works because there's 1 and 1. Now, what would you do for 8? So yeah, so you see you have symmetric odd parts, odd and distinct parts, 7, 1, and then 5, 5, 3. And here we have those diagrams.
I have an idea. Sorry.
Yeah, go ahead. So Eunice first, and then Kyle. So yeah, go ahead.
Oh, so I think it's still about the rule of the power of 2. So for example, this one, you have a 4 here, and you just put this 4 on top of the first column. And for this one, you want to move this 2 on top of the first column.
Yeah, does it work for the rest? How about 12?
So the first one is this 4 on top of here.
Yeah, so that works for this one. Okay. I think it also works for this for the second one. Not really, right? So it kind of already breaks down.
Maybe
here,
you
right?
can. Yeah.
Yeah. So I try to think easier, like simpler than that. Eunice, you wanted to say something? A different idea?
I was just gonna say that like for the even numbers, it's like a straight line, but then it has like one block at the end.
Yeah, that is right. Yeah, so it has, and then good. So it does a straight line, one block and end. And then what about the symmetric part? So for odd guys, we just have a hook or hooks, right? And then for even, we have this one in the middle, right? So there's like a hook, and then you put one here, right? So here there's a. So yeah, let's try to focus on that. So say for 12, right? We have 11, 1. And then there's a hook plus 1, right? Same works for 10. Maybe it will get you something.
Yeah, I think it is like professor. I think that for like odd and distinct, you can just like an odd column.
Like, draw it or just
I can draw it. Like for this column, there is 7 boxes. You can just like fold it.
Yeah, right, because it's an odd number. There's always a block in the middle, and you can fold it around that block, right? So indeed, so you can
there's one here,
so
and
there's 7, and then you would fold it over the middle block, right? So this middle block is over here, this one, right? And you would fold it over. Excellent. Okay, so let's see how this plays out next.
If there is multiple columns, you can just fold it above. I'm not sure how to say that, but
okay. Can you draw maybe? So say to which partition this hook go? To the first one? What's the second one?
I can take second as an example. For this, like this column, there is 5 boxes, and you can just fold it like there is one.
So are you annotating? I don't see any. Now I see it. Yeah, good.
And there is 4 left, so we can just put 2 of it above it, and 2 of it at its right, because the number of the boxes in a column is odd. So when we put 1 in the left bottom, the rest must be divisible by 2. So
right. So because odd number. So this hook goes to
go for
this column, right?
if there is
Okay.
multiple column, we can just
And
put
then
it
this
here.
hook goes to this column, right?
So there is like 1-1 correspondence.
Right, right. So basically, it's because all those parts are odd. They always have a middle block, and we can make a hook out of those blocks, and then we can just connect those hooks. So, for example, this hook goes here, right? Yes, that's right. And there's just one when it just stays the same, right? And this is the case here. There's one here, right? And then there's a hook here, right? And so on. So so those will be mapped to yeah. So that's exactly right. So as you can see, you don't need to know any mathematics to prove it, right? It's like you can give it to an elementary school student and they should be able to do it. In fact, in Berkeley, we have Math Circle, and I taught it to elementary kids, and they figured it out, right? So this, and then you would do this hook goes here. We can do it all day long, right? So it's so much fun. So there's one hook here, one there, right? And then one hook here, one hook there. So the proof is the picture, right? So yeah. So see, it's like, of course, if you try to formulate the dictionary using the numbers, it's going to be very complicated, right? So write a formula that might say this partition to that partition. It's not so easy. But what with pictures, it's pretty straightforward. Yeah. Yeah. So this is the matching, and so obviously it works both directions. Right. So you just bend those hooks. Now this is here. There are some examples, right? So we can use it to calculate various sums, right? So for example, so say we take those. There's this famous triangular numbers. So it's a number which is obtained by counting blocks or marbles, which you can arrange in the shape of a triangle. So you can either arrange them in a regular triangle or as this right triangle over here, right? So how many boxes are in this triangle? So the columns goes from 1 to 13. What's the total number of boxes? Can you say without counting? How much is 1 plus 2 plus etc. plus 13?
91.
Right, so it's 13, right, times 14 divided by 2, right, which is 13 times 7, it's 91. Yeah, so this is the n times n plus 1 over 2. And so you can see that this formula, so that's because of this rule, right, which we did with hooks, right, it's the same. So you can basically take this column, you bend it like that, right? So this allows you to calculate the sum 1 plus 5 plus 9, etc. plus 25. So yeah, so the total number of boxes here is the same as total number of boxes here, and this is equal to 91. Or you can do square numbers, right? So see here, if with the triangular numbers, like the height, yeah, so on odd and distinct part, the height of the columns were changed in increments of 4, right? And as you fold them, you get the staircase. Now you can see if you change them in increments of 2, then as you fold them, you're going to get a square, right? So you have 100 blocks here, which is so-called square number, right? And then those sums will be add up together. So those numbers will be important later when we prove the formula for the P of n recursive formula. So if you haven't seen them before, I just want to show you again. So these are triangular numbers, but the idea is very simple. You just draw them as a triangle and count the number of boxes. And these are square numbers, which is just a square of length n. Okay. Good. So we have some more time. Okay. Any questions so far? No. Okay, so well, I can give you this as a simple homework, but it should be a piece of cake for all of you. So computing those sums using the using those rules. Right? Of course you can compute them using Gauss method, right? Take the one first and the last one, take the second and the one before last, and then pair together. But compute them using this dictionary. Okay. Okay. Now we can ask. Well, let's do maybe. Okay, we have this exercise. Now let's check divisibility by 3. Look at parts which are divisible by 3. So again, there'll be 2 sets of partitions. Partitions of n whose parts are not divisible by 3, not divisible by 3. Right? And compare those with partitions of n with each part is not repeated 3 or more times, which means that a partition, say 1, 1, say 2, 2, 1 is okay because each of those parts is repeated twice, not thrice. So this one is okay, but say this one is not, right? Because a part is repeated 3 or more times. Okay. So let's do another exercise. I think for this one, we'll you just open Mathematica because you have to count a bit higher. Screen. So let's do maybe 15. Oops. Okay. Now you see that you don't have to count too far. Then I'll give you. We can do this one exercise here, and then will be some more for the homework. Yeah. So do you have Mathematica on your computers? If not, I can send you the link to the website. It just will easy to do. So there's a website, Wolfram Alpha. Just one second, let me send you the chat. Which is just the online platform to use Mathematica. Actually, I thought so. It's a question to the administrator that you guys will get access to Mathematica. Is that right, Richard?
It was listed in their material sheet, so all the students should be going onto the website and downloading it. Yes.
Oh, good. So yeah, so then you should be able to get the license key, right? So they should get the Mathematica, right? So then you should go just to website and download Mathematica. I mean, it's not like you have to use it for this course, but it's like it's very convenient. Like I use Mathematica a lot for my research. And yeah, so
their regular PC Jordan will be reaching out to each of them individually to assist with that if there's any issues.
Awesome. Yeah, thank you. Yeah, so I highly recommend. Actually, I think I sent the message not to everybody, but only to one person. Yeah, so here's the link, and then so you can use it online, or you can download the app and use it on your computer. It will be, of course, much faster. Okay, so now here you can just annotate on top of the screen. So maybe 14 is enough. Yeah, let's probably 14 should be okay, right? So yeah, let's maybe start with 14. So I circle partitions which are parts whose parts are not divisible by 3. That's the first exercise. And second, show the partitions where the part is repeated not more than 3 times. So, for example, those long partitions that clearly they're not going to work, right? Because we can here the repetitions is very long. So actually maybe 13 is okay. Yeah, let's start with 13. Yeah, so yeah, okay, good. Actually it might be 12. Sorry. Yeah, let's do with 12, right? So first, so there are 2 types of partitions. Those where parts are not repeated, so but parts are repeated 2 times, 2 times or 1 time, right? So not 3 or more, and those whose parts are not divisible by 3. All of those parts not divisible by 3. For example, 12 is not going to work for that category. Yeah, then there'll be some of them are of both types, right? So in this case, there'll be quite a bit of partitions which are of both types, which are not divisible by 3, right? And then which are where the repetitive part is not repeated three or more times. Or maybe you should use the same color. So the blue are those which are not divisible by 3, right? And then, okay, so far they're all, okay, so I think they're all so far not divisible by 3. I don't know. Okay, probably should have picked a smaller number still. Instead of. Yes, all those long partitions would do, right? Yeah, so basically those, yeah, so first we count partitions that do not contain 3s, 6s, or 9s in them, right? These are those I think that have been highlighted. In fact, I think let me do the sort of, let's keep it for, in order to avoid overcrowding, I'm just gonna copy it. And now let's highlight partitions which are, well, the second property, right? So which are not repeated more than 3 times, 2 times or more. So obviously those strings with many ones, they're not going to fly, right? Yeah. So as long as you have, it's easy to start from the left. Yeah, and then we need to count. So so we're getting towards the end of the first lecture. So yeah, so this will go to the I'm sorry, guys. Somehow I got cut off on my computer. I'm not sure what's going on. Yeah. So so since it's like last couple of minutes, and so this will be the first homework. So I guess I'll send you some more homework, over the email. So yeah. So our next exercise will be to count partitions of each type, and then see if there's a pattern, and then try to identify them. So we expect that the the numbers will be the same again. Can you guys hear me? Hello?
Yes.
Yeah, good. Great. So yeah, so please, I'll send you the lists of partitions. But if you have Mathematica, it will be better if you can just play yourself. You can use them to generate those lists. So that will be the divisibility by 3, and then you can play the same game with divisibility by 4. So you can count partitions whose parts are not divisible by 4, and count partitions where you have repetition not more than 3 times, right? So no 4 and so on, and then you can do it for every number. Right? So that will be the goal of the exercise. Okay, sounds good. Good. So I think we can adjourn. So we have a productive first lecture. So I guess I'll see you guys next week. Thank you. Bye.
Next week.
Bye.
Thank you so much.
Thank
Bye.
you.
Bye. Goodbye.
Thank you. Goodbye.